Hello, everyone. Thanks, John, for that great intro. David's office is a treasure trove with just amazing relics. So today we're going to be talking about XR for space operations. How can we augment situational awareness and decision making? First off, a little bit about me. Clicker, please. No? There we go. So I'm a grad student here in electrical engineering and computer science. I work in Aerowastra as well. I wear a lot of different hats here at MIT. First one is I helped found VR AR MIT, which is a student group here on campus. Clicker, cooperate. Yes. We do all sorts of things AR and VR here. We run a studio. We helped teach the first ever 4-credit VR development class. We also do our own development and do lots of different projects. And another hat I get to wear is I helped direct the MIT Reality Hack this past year. We just had it just about 3 weeks ago here on the 6th floor of the Media Lab. It was a fantastic event. We had over 330 participants and 80 open-sourced XR projects, AR and VR projects that came out of it. They're all up, available for viewing online. Try this one. There we go. And the hat that's most relevant for today and what I'll be talking about is do you guys have an alternate clicker by any chance? So I'm a graduate student here with the MIT Human Systems Lab, which is a part of Aerowastra with a focus on decision making and situational awareness, and using XR to augment our space operations for human spaceflight and other human operations. And today we'll be talking about three different projects that we've worked on. We have an alternate for the alternate. So we talked about 3 different projects, and 2 of them are AR, and 1 of them is VR with sort of a hybrid. So try to get through it and get through all of them. Can we go next? Yeah. Great. So the first one is Hollow Sextant, which is navigational assistance in treacherous terrains. This was done with a focus on Mars. Next. So we did this as part of the NASA Basalt program. And NASA Basalt is one of several NASA analog missions. And the goal with an analog mission is to test different technological capabilities, one, that we'll need for doing future human spaceflight, this one with a focus on Mars. And we asked 2 research questions. The first is, what do we need to do real good science on Mars? And how are we going to have Earth scientists help and coordinate and collaborate on Mars? The second is, what are the technological capabilities that we need? Next. So the first problem is Mars is very, very far. This is a known fact for all of us. In fact, it takes up to 20 minutes for a single message to go one way from here to Mars. Now, this puts a lot of strain in the way that we operate and the way that our astronauts operate. This requires them to be a lot more autonomous, be able to make decisions on their own, process data on their own, and remove the reliance that they have on mission control. Now, the second is that the mission durations for a Mars mission are also going to be much longer. We're looking at days that they might spend outside, a lot more science they need to do than the current missions that we've done. Next. So with NASA Basalt, we simulate a Mars mission. We spend 2 weeks in Mars-like conditions effectively and test the human dynamics and the different systems that we need. So what we do is we have 3 teams. The first team is a Mission Support Center on Earth. We have them on Earth time. They're simulating a mission control center. And then we have 2 teams that are on Mars. One team is intravehicular. They're in a habitat effectively. They're coordinating with both between Earth and the team that's out on the field. The third team is our field team. These are crew members that we have who go out on the field and do testing for 8 hours a day over the 2-week period. They've got backpacks on with all the communications and instrumentation and everything they need. And they're out there collecting samples, going from site to site, and doing all of that. And they bring it back at night. All of it gets analyzed. We do real science as part of this, even though it's a simulation, and then analyze where to go the next day and find the next field site. So this was done at the Kiowa volcano in Hawaii. where we were doing field tests for the geology and the astrobiology of the location. As part of this, of course, we were testing different technologies each day as they would go about doing their science. So HoloSextant as a tool is a navigational assistant. So effectively, it was a spatialized path that would overlay and help our crew members go from site to site on their way when they're collecting samples. Now, what it uses is a backend called Sextant, which automatically generates the most optimized path for humans to go from point A to point B. It takes in the terrain data, obstacle data, human metabolic functions, and calculates what's the best way to go from A to B. And this is important for astronauts when you think about conserving resources, and especially in contingency scenarios, when they have to get back to safety if there's any issues. But we say a path is only as good as its interface. And this extends to other pieces of data, but this is where we brought in HoloSextant. In the past, Apollo 14, in fact, astronauts used paper maps, got lost, and no one knew how to help them, and they had to figure out their way. And you can imagine taking a wrong turn on Mars would not be as easy as taking the next exit. And in more recent times, we've had wrist displays, we've had other kinds of visual interfaces, but we wanted to see what we could do with augmented reality to provide the data to our crew members. So we built an AR interface that would overlay on the user's environment and use actual terrain data that we have from before, taking the Sextant's path. And our biggest design goal here was to have a very, very minimal interface. We wanted to reduce visual clutter, so really all we had was a path and some optional additional information they can pull up and request if they want to. A big focus area here for us was how do we calibrate this. So effectively, the user would put on the headset, get geared up, and they would go through a minimal calibration process and then be ready to walk along the path and follow the path that's being rendered. They would have to do some recalibration on the fly, but we tried to design it so it had minimal user input, didn't require their hands, and they could simply just walk along the path. So this is actually one of the example path traversals that we had with some odd text above it. But what we see here is the yellow is the actual path that they took, and the orange was the path that Sextant gave us that said it was the most optimal path. And we can see that they actually followed it quite well. We had about over 90% accuracy with this. And what's interesting about this example that you can't see here, it's about 400 meters from start to end, 450 meters or so. There's quite a bit of height elevation as well. And this turning sort of S-shaped path is the only way to go from start to end. That's because this right here is actually a lava channel that was forged by when lava had flowed through this location. And this hill basically got carved out, and there's only one way to go from start to end. And even if you went misstepped a little bit, you'd have to backtrace your steps to go back down this way. And we'd actually, you could run through. We ran some experiments with people, and this was the only way they could get there. On the right here, we have former astronaut Stan Love wearing our system and using it. And we learned some interesting qualitative things from running people through it. So Stan, as an example, he put on the headset. The first thing he did was raise the path 6 feet in the air. Then he tilted his headset to not be in front of his eyes. So we asked Stan, what are you doing? And he told us, I want nothing obstructing my field of view, not even this headset. That's transparent. I want to be able to see the ground. I want to be able to see where I step, make sure that I'm not stepping anywhere incorrectly. And then I want to be able to look up in the air and see where the path is if I want to look at it. But I want to make that decision. And this was really interesting to us because we hadn't expected that at all. We imagined everybody wanting it on the ground. Most people did. But the ultimate takeaway for us was personalizable user interfaces were really important. Different users wanted different things, so we built in the tools that allowed them to change the interface in certain small ways that made it more comfortable for them. Especially now, without having actual design standards in AR and VR, this is very important for us to be able to cater to different needs of people. So next up, we're going to talk about our second project, which is a project we did for AR suit diagnostics and astronaut task guidance. So this one, we started with a We started with a NASA-built task board. This is designed to simulate tasks that would be done at 0G. So a lot of the users would strap in, they would strap their tools in, and they would then go about doing a task. So an example task would be rerouting power line or changing a fuse. And these tasks would be about 15 to 25 steps long. So long enough that it's tough to memorize, but not too long that would take you an hour to do it. So the first thing we did was we built an AR tool to guide our crew member through this. So we had an animated digital replica of our task board. So this would show each step along the way, and it would show exactly what the movements you had to do or what you had to change, and highlight the objects that you needed to find on your physical board. We had audio instructions that would walk our users through, and this was very familiar to them, similar to how they get current audio instructions through the radio. And we had a text follow along with bullet points that they could always refer to if they needed to. So this was the task guidance part. And the second piece was the suit diagnostics. So we built a system that would simulate a suit's parameters and the change over time, over 24 hours, and we would show that in real time to our users who weren't wearing suits, but they would be able to view that data as if they were wearing a suit. We had two interfaces, one which was more minimal and one which was would showcase all of the data. And we would do anomaly detection on the data to point out any alerts as they needed. So for example, your oxygen is dropping, your battery consumption rate is too high, you might want to take action on it, depending on what is causing that. So we tested a combination of the task performance of these users combined with, are they looking at their data, are they catching alerts as they happen, and how responsive are they? The combination of these two tasks was always important to us. So we tested this at NASA Johnson Space Center with a couple of NASA's human study candidates, and we got some interesting results. So we found that users had increased comfort with the task. They were more willing to ask the tool to repeat a step, for example. They were more willing to rewatch a step, go back a step, because it was much more automated and didn't have a human that they were asking to do that. And this led to improved autonomy. They felt comfortable that they could take this task and do it again without the tool if they had to, compared to following paper instructions or just audio instructions. We had inconclusive results on the actual cognitive workloads from our tests. I think we need possibly better hardware and better tools to study that. That might need to be built for AR and VR that we don't have today. But the most important takeaway was that multi-channel sensory input was what really drove this home. The fact that I mentioned before, there was audio, there was text, and there was visuals, meant that users could capture this information and retain more of it, one per channel that they consumed it from. So I think that was what combined all of the features of the tool and made it better than just using audio or just using text. So moving on to our last tool, we're going to be talking about something we're working on currently called VMCC, which stands for Virtual Mission Command Center. This is focused on simulating multi-user mission control scenarios. So if we take a mission control center and say, what does it actually mean? It has three components. First is we're talking about lots of data. We're talking about co-located personnel and some experts that we might remote in, and time-critical decisions. This is what usually leads to a need for a mission control center, a physical space where people are processing data, understanding it, and making decisions based off of it. So we wanted to look at how have mission control, what's existed in mission control over the past several decades. And it hasn't changed a whole lot since conception. It's still a lot of monitors, a lot of computers, a lot of people. So we wanted to think about what does the future of this look like for future planetary space missions and other operations. So we analyzed lots of analog missions from the past. We analyzed Apollo missions to understand what we need to go forward. And we said, what if we could build a simulation of a mission command center that we can use to test and learn about people going through it, understand the human dynamics better, understand their relationship with the architecture, with the tools they're using, instead of building a physical center first. So that was what VMCC, that's how it started. And it's got three components. So we designed a mission control that was a hybrid of some new concepts and some existing modalities that people are familiar with to see, okay, if we run people through this, what can we learn out of it? The first piece is traditional workstations. So people can work at their desk as a traditional workstation with tools they're familiar with and using software that we've built over the past several decades. The second is a feed of critical information. This is information that everybody in the room needs to know, needs to follow along, so timers, playbooks, any information from workstation that is worthy to throw up. And lastly is our center console. This is a 3D data visualization hub. Essentially, this is where the decisions are going to get made. Our users will stand around and huddle around different types of data. For example, we can have models of terrain data. We can have rover navigation data. We can have spatially tagged instrumentation data, so spectrometer data that's tied to the sampling site, tied to the terrain that you captured it at. So we can combine all of that and create sort of an added dimension to the visualization that helps make faster, better decisions. So we set out to build this, and this is a high-level picture of what VMCC is going to look like. It's a single environment that's going to be a hybrid virtual and physical environment. It's going to be, your users are going to be able to go between virtual workstations and their center console and the critical feed. Now, we're bringing in architecture from the room, so the room will have tables and chairs that are all physical that users will be able to use, and the displays and visualizations will all be virtual. So right now what we have is a sort of a multi-user sandbox environment that we're using to study the interactions and study how exactly are users using body language, how are they communicating, what is the fidelity that we need to build in. So we're starting at a very basic level and really understanding what the communication looks like, how are they making decisions. And our goal is to have a pilot study done by the end of this year, and hopefully be able to really run an existing mission scenario through the system and gather a lot more data onto what we need and what are the criteria we need for data visualization for the future. Now, VMCC is a research tool, but I want to leave you with one last bit, which is what it could become if it was a rapidly deployable actual command center. Take a disaster recovery zone, somewhere that's been hit by an earthquake or a tsunami, and you have lots of resources piling in from around the world. People, money, food, medical equipment, all sorts of things. And there's a lot of data and a lot of important decisions that need to get made. Now, let's imagine a team can walk in, take over an empty room, walk in with 2 Pelican briefcases with headsets. 20 minutes, and they're set up with a state-of-the-art data command and control center that allows them to view all the different pieces that are moving on the field, allow them to make decisions on the fly, make it modular, and be able to adapt it for any situation and use it. Effectively take what we have at Johnson Space Center that we use to command spaceflight and take it and make it deployable for anywhere to process the data that we need. So this is kind of the vision for VMCC that we can really build out and help empower people to make better decisions. But right now, we're focused on the learnings we can get from running users through it and what they can get. So that's it for today. Again, I'm Eswar. Feel free to tweet at me or flag me down. Happy to talk about any of this. The first 2 projects have both been published, so I'm happy to share links to our research and the extensive data that we actually have on it. Yeah, thank you.